The first kind of example problem we can consider involving the idea of continuity would just be a question that asks about any points of discontinuity. So for example, f of x equals negative 3x squared minus 5x plus 1. This is a polynomial, and that means that it will always meet our definition of continuity. The limit as x approaches c will always exist, f of c will always exist, and the limit as x approaches c of f of x will always equal f of c. So there are no points of discontinuity for something like this. We could have a rational function, f of x equals x minus 2 over x squared minus 4. And this would be discontinuous at any place where the denominator equals 0, or wherever x squared minus 4 equals 0. And this occurs because this factors into x minus 2 times x plus 2. We would have points of discontinuity at x equals 2 and x equals negative 2. The next problem, asking again about points of discontinuity. If f of x equals the cube root of x squared plus 2x minus 1, this is continuous everywhere because it's an odd root. So there are no points of discontinuity. Finally, we could consider the function the square root of x squared minus x minus 6. And whenever this x squared minus x minus 6 is less than 0, this will be discontinuous. If I factor this, I get x minus 3 times x plus 2. And I want to know, when is this less than 0? Well, I know it will equal 0 at x equals 3 and x equals negative 2. So I'm going to do what's called sign analysis to help me make sense of this. I know at these 2 points is where it equals 0. And I want to know what's happening between those 2 points. So I can just test some numbers. If I try negative 3 as an example, I'll substitute it back into this form. This will give me negative 6 times negative 1, and negative 6 times negative 1 is a positive number. So I know that for any value less than negative 2, this function is positive or greater than 0. If I test the number 0, because it's between negative 2 and 3, I end up with negative 3 times 2, which is negative 6, and that means it's negative in that range. Finally, I'll test the number 4. That will give me 1 times 6, which is 6, and that's positive. So I know that my original function will be less than 0, and therefore in this case discontinuous when x is between negative 2 and 3. Another way to consider the same thing is I know that the x-intercepts of this graph are at negative 2 and positive 3, and since it's a parabola opening up, graphically I know that this is the area where it's less than 0. So that's one kind of problem, just simply finding points of discontinuity. Another kind of problem is similar, except we need to find some things out about piecewise functions. So let's consider the piecewise function f of x equals x squared minus 3 whenever x is greater than or equal to 1, and 1 minus x whenever x is less than 1. Algebraically, notice that at 1, x squared minus 3 would have the value of 1 squared minus 3, or negative 2, and 1 minus x at 1 would have a value of 1 minus 1, or 0. So just based on that algebra, I would conclude that this is discontinuous at x equals 1. Right, graphically, what this thing would look like is it's the parabola x squared minus 3 from 1 and on. So if we were just to plot some points, it would be 1, negative 2, and then say 2, 1, and it's going to have this kind of shape to it. And before 1, we'll be using 1 minus x, and 1 minus x is a linear equation that has a y-intercept of 1 and the slope of negative 1. So the graph looks something like this. So we can see graphically it's discontinuous, and algebraically we showed why it must be discontinuous. Let's contrast that with a different piecewise function. F of x equals x squared plus 3x minus 2 and negative x squared. It's the first when x is greater than or equal to negative 2, and the second whenever x is less than negative 2. Notice that if we test what's happening at the value of x equals negative 2, we have x squared plus 3x minus 2, which will become 4 minus 6 minus 2, or be negative 4. And if we test negative x squared when x is negative 2, that gives us negative 4 as well. So algebraically, this is continuous at x equals negative 2. Alright, so to evaluate something via piecewise, that's a piecewise function, we would just need to see that at the point where the rule changes, do you have the same value? Finally, let's consider a more abstract kind of problem where we need to figure out what value of some constant allows something to be continuous. So let's consider the function f of x equals 3x plus 2 whenever x is less than or greater than or equal to 1, and is 2k minus x whenever x is less than 1. I know the point of discontinuity is potentially at 1, but 3x plus 2 when x is 1 has a value of 5. So I want to know, when is 2k minus x equal to 5? And more importantly, what value of k, when x has a value of 1, causes this to equal 5? Solving for k, we'd find that it is when k equals 3 that we have a continuous function, and for any other value of k, we would have a discontinuous function. Let's consider one more problem similar to that. So we have a function, it's piecewise. We'll use the rule kx squared whenever x is greater than or equal to 2, and we'll use kx minus 6 whenever x is less than 2. Well, I know kx squared when x has a value of 2 will equal 4k. So I want to know for kx minus 6 when x has a value of 2, when will that also equal 4k? And if I solve this equation for k, I will find that this happens whenever k has a value of negative 3. Or more importantly, another thing that I'm saying is that f of x is continuous when the rule is negative 3x squared whenever x is greater than or equal to 2, and when the rule is negative 3x minus 6 whenever x is less than 2. So there are some problems involving the idea of continuity, and in the next session of our video for this section we'll be considering the relationship between differentiability and continuity.